Assalamualaikum. This is your mentor Dr. Verdha and welcome to another lecture. This lecture is about vaporizers. So what are vaporizers? Vaporizers are devices that are used to deliver a precise and accurate concentration of anesthetic vapor and compensating for variables like temperature, pressure and fresh gas flow. So what is their classification? We can classify vaporizer according to different methods. The first is by the mechanism of adding vapor. So there are two classifications: variable bypass and measured flow. Variable bypass is the most common type, which splits the fresh gas flow, and a portion is saturated with the vapor in the chamber, which then recombines with the bypassed gas. The splitting ratio is fixed, so the output concentration is stable regardless of the total fresh gas flow. The other is measured flow vaporizers, which is specifically true for desflurane, the Tech 6, which injects a precise separate stream of vapor into the fresh gas flow, and it requires automated compensation for changes in fresh gas flow. The second mechanism of classification is by internal resistance. They are either low resistance or high resistance. The low resistance vaporizers are also called as drawer vaporizers, which are placed inside the breathing system. They are also called vaporizer in circuit or wick. And the patient's effort draws the gas through it. They are usually used in field and portable systems. And the examples include Oxford miniature vaporizer, but their concentration is less accurate. The most commonly used are high resistance plenum vaporizers. The Tech 5 and Tech 7, which we use in the modern anesthesia machine, are high resistance plenum vaporizers. They are placed outside the breathing system on the machine's back bar, and they are also called a vaporizer out of circuit or VOC. And they require pressurized gas flow, continuous flow machine, and they are more accurate and common in hospitals like Tech 5 and Aladdin acid. The third classification is by temperature compensation. So there are two methods, either by heat sink or by automatic adjustment. The heat sink usually uses a large thermal mass like a metal casing to absorb the heat and slow down the cooling, while the automatic adjustment actively alters the splitting ratio as the temperature drops, either by using bimetallic strips, which are mechanically adjust the gas flow, by the bellows, or by the electronic control. Then the fourth system is classified by location. Vaporizer classified by location. They are either inside the breathing system, vaporizer in circuit or wick, in which the driving force is the patient's inspiratory effort. Their resistance is very low, and the design is simple, lightweight, and they are often agent non-specific and inexpensive. They are primarily used for field or for portable machines used in difficult environment. But the limitation is that their performance is very less efficient, and it can be affected by cooling of the agent. The examples include Goldman vaporizer and Oxford miniature vaporizers. The Diamedica vaporizer is a hybrid. It's low resistance, thermally stable, but can also be function as plenum vaporizer. ठीक है, तो Diamedica जो vaporizer है, it is special. It is hybrid. This here shows the Diamedica vaporizer. Then in the other vaporizer in the classification by location is the outside the breathing system vaporizer, out of circuit vaporizer. Their driving force is pressurized gas supply from the anesthesia machine. They are high resistance and reliable, easy to use, and agent specific. They are standard for hospital continuous flow machines, and they are more accurate and feature temperature compensation. Examples include the Tech series and the Aladdin cassettes. Now, what are the characteristics of an ideal vaporizer? This is a question that comes frequently in the Viva exam. So let's discuss that. So for the performance, An ideal vaporizer's performance should be unaffected by changes in fresh gas flow, volume of liquid agent, ambient temperature and pressure, cooling from the vaporization, and the pressure fluctuation from the mode of respiration or by the ventilator. Then their design should be low resistance to gas flow. They should be lightweight and require only a small volume of liquid agent. For their construction safety, they should be made from corrosion and solvent resistant material. They should be economic and safe to use and require minimal servicing. Now let's discuss all the vaporizers one by one and discussing their physics and their design components. So the most common vaporizer in use today is the plenum vaporizer. It is a variable bypass system that splits the fresh gas flow into a bypass channel and a vaporizing channel. For the vaporizing chamber, it contains wick or baffles to maximize the surface area for efficient vaporizing. It is temperature compensated, which uses a bimetallic strip or bellows to automatically adjust the gas splitting ratio as the liquid agent cools. The bimetallic strip used in vaporizer is made of two bonded metal strips with different coefficient of thermal expansion. Either, for example, for usually brass and invar se bani hoti hai, theek hai? It acts as a temperature sensitive valve for automatic temperature compensation. As the temperature drops, the strip bends, altering the gas splitting ratio to allow more flow through the vaporizing chamber, so maintaining a constant output concentration. This picture shows a bimetallic strip. As the temperature drops, the strip bends, opening the gas flow and allowing more gas flow through the vaporizing chamber. So what are the placement evolution through the ages? In the older designs for Tech MK2, it was positioned inside the vaporizing chamber. For modern design, for Tech MK3, 4, 5 and 7 in Sigma Delta, it is positioned outside the vaporizing chamber. The reason for change is that moving the strip outside the chamber likely improves longevity and reliability by protecting it from direct contact with the corrosive mixture of oxygen and volatile agents, which could cause corrosion or sticking, as was a risk in Tech 2. So the plan, and this is a schematic of a plenum vaporizer. As you can see, this is the casing. This is the vaporizing chamber. This is the bypass route. The fresh gas comes in from here. There the flow is split into the vaporizing chamber and the bypass chamber. As the temperature cools down, this is the bimetallic strip which bends and allows more gas to flow into the vaporizing chamber. And the vaporizing chamber gas comes into the vaporizing chamber and carries the vapor and goes out into the concentration dial, where we percentage control valve, where we control the concentration of the vapors. And then it comes out and combines with the bypass flow and comes out of the vaporizer outlet port. The vaporizer is made of high thermal capacity materials like copper, which acts as a heat sink. And it uses an interlocking system, the selectatic system, to prevent more than one vaporizer from being turned on simultaneously and ensures a gas-tight seal. The interlocking selectatic vaporizer manifold system has two male valve ports with an O-ring for a gas-tight fit to take the vaporizer's two female port. This is the picture showing the selectatic series manifold. These are the male valve ports which take the two female ports from the vaporizer, and around it there is the O-ring which ensures a gas tight seal. The vaporizer safety interlock system includes a control dial lock The percentage control dial lock is mechanically locked and it cannot be turned unless the locking lever on the mounting system is properly engaged. Then it also has interlocking rods. An interlocking rod mechanism physically prevents more than one vaporizer on the back bar from being turned on at the same time. This stops agent from one vaporizer contaminating another downstream. And it also has a gas flow control. The fresh gas flow only enters the vaporizer when it is switched to the on position. This ensures that no gas passes through an inactive vaporizer. So these three are the vaporizer safety interlock system. Now what is its mechanism of action? All the planar vaporizers are agent specific. Each vaporizer is calibrated for a specific volatile and static agent. You cannot interchange the volatile agent. And all has gas flow splitting. The incoming fresh gas flow is split into two streams. A major bypass stream and a minor stream, which is typically less than 20% that enters the vaporizing chamber. The vaporizing chamber is designed using wicks, baffles or bubblers to ensure that the gas leaving it is fully saturated with the vapor before mixing with the bypass gas. They all have concentration control. The percentage control dial adjusts the splitting ratio between the bypass and the vaporizing chamber flows, setting the final output concentration. They have flow independence. In the modern design, the output concentration is stable across the wide fresh gas flow range, which is usually 250 milliliters per minute to 15 liters per minute. They all are temperature compensated. That is, they are compensated for cooling from vaporizing, which lowers the agent's saturated vapor pressure via two methods. Either via heat sink. A high thermal mass casing, usually made of copper, supplies the heat, and by the automatic adjustment, a temperature sensitive valve, which either consists of bimetallic strip or bellows, automatically increases the flow to the vaporizing chamber as the temperature drops, maintaining a constant output. For the altitude or pressure effects, at high altitude or low ambient pressure, the volume percent of the vapor delivered is higher for the same dial setting, but the partial pressure and the clinical effect remains similar. The opposite occurs in the hyperbaric condition. So clinically, the partial pressure is what matters. So these changes are not practically significant. The key safety features and problems involved in the planar vaporizer are the spillage risk. The modern vaporizers, Tech 5 and above, have an anti-spill valve to prevent liquid agent from entering the bypass channel if tipped. Historically, older designs could deliver dangerously high concentration if spilled. So if tipped, purge with 5 liter per minute fresh gas flow at 5% dial setting for 30 minutes. This was the safety practice. They also had leak potential, but the Selectatix mounting system that relies on the O-ring, which can be damaged or dislodged during vaporizer changes, thus creating a potential leak source. There are also back pressure effects from the ventilator, especially the minute volume divider ventilator. Which cause pressure fluctuation that can force the gas back into the vaporizer. And this retrograde flow can lead to increased and potentially toxic agent concentration. Then there are some compensation mechanism involved. For example, there is a long inlet port in Tech 3 which protects the bypass channel. The downstream flow restrictors that maintain higher vaporizer pressure, and the equal volume bypass and vaporizing chambers. For maintenance and contamination, preservatives like thymol and halothane could accumulate on the wicks and can cause mechanical sticking, especially of bimetallic strips in older models like Tech 2. But the modern agents are preservative free, thus eliminating this issue. But regular servicing is required to maintain accuracy. The key safety features involved in the vaporizer are pressure relief valve, which are located downstream, and opens at 35 kilopascal to protect the flow meters in vaporizer from overpressure if the outlet is blocked, especially in minute volume divider. Then the bimetallic strip relocation, they are moved outside the vaporizing chamber since step 3 to prevent corrosion from the direct contact with the agent and oxygen mixture. At extreme ambient temperature, they can still affect output accuracy despite temperature compensation. And the vaporizer accuracy is not guaranteed outside its designated operational parameters. The vaporizing filling devices are used to safely and accurately fill vaporizers with the correct volatile and static agent. They have some core safety mechanism to ensure that the correct key agent is used for correct volatile and static. For example, they have agent specific keyed opening. Each filler has a unique geometric shape that only fits the matching port on the correct vaporizer and agent bottle, preventing dangerous cross-filling of the agent. They also have spillage prevention. They are designed to minimize the spills during the filling process. And they also have overflow prevention. Integrated systems ensure that vaporizers cannot be overfilled. There are some special designs for modern agents like desflurane and sevoflurane. These fillers have valves that only open when fully inserted, providing an extra layer of spill protection. They have standard color coding. Halothane is red, enflurane is orange, isoflurane is purple, sevoflurane is yellow, and desflurane is blue. In the modern filling keys, their innovative feature is anti-pollution cap that allows the filler to be left attached to the bottle between uses. Benefits क्या होते हैं उसके? They prevent agent vaporization, eliminating airlocks for faster filling, and enable complete emptying of the bottle to reduce waste. Now let's discuss some modern variable bypass vaporizer like Tech 5. It is basically a high resistance plenum vaporizer which is mounted outside the breathing circuit. It is a standard device for delivering a safe, accurate, and precise concentration of a specific volatile anesthetic agent like sevoflurane or isoflurane via continuous flow and static machine. Now, how it works? It basically works by gas splitting. The fresh gas flow enters and is split into a bypass stream, which is the majority, more than 80%, and a vaporizing stream. A small portion of the fresh gas flow is diverted into the vaporization chamber. The vaporizing in the chamber, the gas flows over the wicks and baffles to maximize surface area and become fully saturated with vapors at the agent's saturated vapor pressure. And the concentration control dial, the saturated vapor is diluted by the bypass gas when the stream recombines. The control dial adjusts the splitting ratio between these streams to set the final output concentration. They are temperature compensated because the vaporization causes cooling, which lowers the saturated vapor pressure and reduces the output. For solution, we have incorporated heat sink, which is a large copper casing which absorbs and releases the heat to stabilize the temperature. There is also a bimetallic strip which automatically increases the flow to the vaporizing chamber as the temperature drops, maintaining a constant output concentration. The advantages of using Tech 5 high resistant vaporizer is that because they are easy, reliable, and accurate, typically within plus minus 15% of the dial setting of flow between 0.25 to 15 liters per minute, and they require no external power source. Disadvantages क्या हैं इसके? They are heavy and they are not easily portable. They must be used out of circle due to high internal resistance. They have no agent level alarm and the accuracy can falter in extreme ambient temperature. The safety features incorporated into these are they are agent specific, they are calibrated for one agent only, and they have keyed filling system that prevent incorrect filling. They are color coded for quick visual identification, and they have interlocking backbar which prevents more than one vaporizer from being turned on simultaneously. They have anti-spill valves that prevent liquid agent from entering the bypass channel if tipped. And they have mitigation of the pumping effect. The design features, which include long gas conduits, high resistance and non-return valves, minimize dangerous concentration spikes which are caused by pressure fluctuation from ventilators or the oxygen flush. Now, what are the keynotes on vaporizer output and the atmospheric pressure? For standard reference, at sea level, 100 kilopascal, a vapor pressure of 1 kilopascal equals the concentration of 1%. The clinical effect on the patient, which is seen in the patient, is from the partial pressure. The anesthetic effect on the brain is determined by the partial pressure, vapor pressure of the agent, not the volume percentage. The saturated vapor pressure is only dependent on the temperature, but not the ambient atmospheric pressure. Therefore, the partial pressure of the agent delivered from the vaporizing chamber does not change with altitude or in hyperbaric chamber. What is the difference between reading dial and the delivered concentration? The percentage dial on the vaporizer is calibrated for the sea level pressure, which is 100 kilopascal. At high altitude, that is the lower pressure, the same dial setting delivers the same partial pressure but a higher volume percentage. For example, a dial setting of 2% delivers a 2 kilopascal partial pressure. At sea level, and that is 100 kilopascal, 2% setting concentration will deliver 2 kilopascal over 100 kilopascal, while at altitude of 50 kilopascal, 4% concentration will deliver 2 kilopascal of 50, but the same 2 kilopascal partial pressure. Now, what are the practical implications? A vaporizer can be used normally at altitude. The clinical effect, which is induced by the partial pressure, will be as intended based on the dial setting, even though the displayed percentage is inaccurate. So, the user should not adjust the dial to compensate for the atmospheric pressure changes. You will set the dial to the same concentration as you will do at normal sea level. Then there is some difference in the desflurane Tech 6 vaporizer. Let's discuss that. The desflurane vaporizer is a specialized vaporizer designed exclusively for the safe and accurate administration of desflurane, which is an agent that is too much volatile. Its boiling point is at 23.5 degrees centigrade for standard bypass, variable bypass vaporizer. These pictures shows the schematics of a desflurane vaporizer. This is a Penlon Sigma EVA desflurane, and this is a Tech 6 desflurane vaporizer. This is a schematic showing the desflurane vaporizer. There is a heater, the desflurane liquid, desflurane vaporizer, which goes into the desflurane circuit. There is a manual control dial which will set the concentration, and then the fresh gas flow will come in the circuit. There is a differential pressure transducer which will check for its pressure, partial pressure, and the manual control dial will directly inject the desired vapors into the fresh gas flow, which will come out of the common gas outlet. The core design principles of a desflurane Tech 6 vaporizer is that it is electrically heated and pressurized, which heats desflurane to 39 to 42 degrees centigrade, well above its boiling point, and pressurize it to 2 atmosphere in a sealed chamber. Here, there is a pressure of 2 atmosphere. This eliminates the need for temperature compensation. Okay? Then a measured flow injection. Unlike the variable bypass design, the fresh gas flow does not enter the vaporizing chamber. Instead, a precise amount of pure desflurane vapor is injected into the fresh gas flow. Now, how it works? It requires mains electricity with a 9-volt battery backup and a 5 to 10 minute warm up to reach operating temperature before use. A differential pressure transducer constantly compares the pressure of the desflurane vaporizer to the pressure of the fresh gas flow. The concentration dial of 0 to 18% sets the desired output by adjusting the resistor to govern vapor flow. And there is automatic compensation in the desflurane vaporizer. If the fresh gas flow increases, its pressure rises. The transducer detects this and signals a valve to increase the injection rate of the desflurane vapor, maintaining a constant concentration. This process reverses if the fresh gas flow decreases. The advantages of desflurane vaporizer include that it is accurate. It has a comparable accuracy to modern variable bypass vaporizer. It is temperature independent. It is unaffected by ambient temperature changes due to active heating. It is also flow independent. It automatically compensates for variation in the fresh gas flow rate. And it also has integrated alarms which features visual and audible alarms for low agent, no output or malfunction. The disadvantages include that it requires an electric power. It will not function without power, unlike the other tech vaporizers. And it also requires a warm-up time. It cannot be used immediately, requiring a pre-use heating period. The safety features included in this, it has a agent-specific filling. It uses a keyed filling system which is color-coded to prevent filling with the wrong anesthetic agent. It also has spill prevention. It is designed to prevent liquid desflurane from spilling into the fresh gas flow pathway if the vaporizer is tilted or inverted. It also has a safety interlock which mounts on the standard selectatic system, allowing only one vaporizer to be on at a time. Then there is another innovative vaporizer system called as Aladdin cassette vaporizer system. The core concept involved in this, that is, it is an electronically controlled variable bypass vaporizer system which is used in GE ISIS anesthetic machine. It consists of a refillable agent specific cassette, the vaporizing chamber that plugs into a permanent electronic housing on the machine. These are the Aladdin cassettes or different agent specific volatile agents. Now, how it works? The cassette acts as a removable vaporizing chamber. The bypass channel is located in the machine housing and not in the cassette. As you can see in the schematics of the Aladdin cassette, the cassette acts as a vaporizing chamber, and the bypass route is included in the machine housing, which is independent of the cassette. The fresh gas is split and a portion enters the cassette, which becomes fully saturated with the vapor and then recombines with the bypass gas. A CPU uses data from multiple sensors to precisely and rapidly adjust the splitting ratio via solenoid valves, ensuring accurate output regardless of the flow, temperature, or pressure changes. And each cassette is magnetically coded. The machine automatically identifies the agent and configures itself accordingly. Unlike the heated Tech 6 desflurane vaporizer, the desflurane Aladdin cassette works on the same variable bypass principle. Its accurate performance is enabled by rapid computerized second-by-second adjustment to the splitting ratio. The key advantages are its enhanced safety and convenience. The cassette is spill-proof and can be carried in any orientation. Automated agent recognition prevents misuse and is also accurate and automated. Features full electronic temperature, pressure, and flow compensation. And it also has integrated data which provides on-screen information about the agent level and usage. The disadvantages include that is highly machine specific, only compatible with this designated anesthetic workstation, and also power dependent, requires electricity to function and will not operate during a power failure. These are the modern vaporizers that are used. Now let's discuss some historically relevant vaporizer or the first vaporizer systems which were used. So the first of all is the Boyle's bottle.